We're going to learn how to read skeletal line structures, which is a way that organic molecules can be condensed down by omitting all of the carbons and hydrogens and making them implicit using a certain system that has been established. So the easiest way to go about doing this is when you look at a structure where it looks like it's just lines in a couple of letters, if there are any at all, you have to understand that every vertex, like the intersection of two or more lines, and every end of a line represents a carbon. So let's jump right into it. The first example on the left, we're going to identify everywhere a carbon would be, which would be everywhere there's an end or a bend. So right now I've got 1, 2, 3, 4, 5, 6 carbons, 7, 8, 9, 10. So as of now, I know that my formula is C10, and there are going to be some hydrogens. If you look at something and you see no chemical symbols at all, then it is a hydrocarbon of some type. That means it's composed only of carbons and hydrogens. As you can see in the other two examples, the oxygen and the nitrogen in those other two compounds are explicitly shown. And sometimes hydrogen has to be explicitly shown if the hydrogen is connected to a non-carbon atom. But back to the first example. We have 10 carbons. As denoted by there are 10 intersections of lines or ends of lines. Something very important to know about carbon is that it is what I call best friends with hydrogen. If you see a carbon and it looks like there's nothing else around it, then the surrounding atoms are hydrogens. And to determine the number of hydrogens that a particular carbon has, you have to know that carbon can have up to 4 bonds. So let's take a look at this carbon on the very bottom left. This carbon here already has 1 bond connecting itself to another carbon. If carbon can have a maximum of 4 bonds and 1 bond is explicitly shown, that means that there are 3 possible places hydrogen could go. Looking at the second carbon, we have 2 bonds. There is a bond connecting the carbon to the first carbon we just examined, and also that third carbon out there. So because that second green dot, that second carbon, already has 2 explicitly shown black lines that represent the bonds, it can have up to 2 more bond areas, which would be hydrogens because they are hidden. And the same would apply to this carbon. And this carbon in the middle, that seems to be the joiner between 3 different regions, has 3 bonds explicitly shown. That carbon in the middle is connecting to 3 other carbons. And because those 3 bonds are 3 of the 4 possible bonds, that 4th bond is understood to be a hydrogen. Analyzing this, you can see that every complete end will have 3 hydrogens. A carbon that is in between 2 bonds could have 2 hydrogens. A carbon that is connected to 3 other carbons, or has 3 other bonds, would have 1 hydrogen there. This one would have 2. This one would also have 2. This has 2. And every time a carbon is on the end, it has 3. As you'll see in the next example, it is possible for carbon to have no hydrogens on it directly. Let's figure out what the formula is for this compound. Counting them up can be tricky, so you just have to make sure that you don't miss one. So however you want to group them up or have any counting techniques, feel free to do that. After counting up all the hydrogens, you will see that there are 22. So the formula for this alkane is C10H22. An alkane is a hydrocarbon that has no double or triple bonds. Moving on to the second example, we're going to identify all of our carbons. We have 1, 2, 3, 4, 5, 6. So I will write C6, and then we can count up our hydrogens. This carbon here would have 1, 2, 3 hydrogens, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm not actually writing out the H, but I'm going to stick with the color convention, and you can understand that the hydrogens are that pink color. If you look at that very central carbon that is double bond connected to the oxygen, you see that I did not denote that there was a hydrogen there, and that is because there is not a hydrogen there. Looking at how many bonds this carbon has, it has 1, 2, 3, 4. 2 single bonds and a double bond. Because that is 4 bonds connected to that carbon, it can't have any implicit hydrogens because the maximum number of bonds that the carbon would have would be 4. The formula would be C6H12O. The third example is a common medication. It is Adderall. It is a type of amphetamine. And in identifying all of our carbons, we're going to start with this ring. 1, 2, 3, 4, 5, 6, 7, 8, 9. When the end of a line ends with a chemical symbol or a chemical group called a functional group, that does not mean that there is a carbon there. Sometimes carbons are explicitly shown, but they can be omitted or shown. It depends on different factors about what the person is trying to convey with that compound. We have 6 plus 3 is 9 carbons on this compound. So we're going to write C9. In counting our hydrogens, we know that carbon can have up to 4 bonds. So there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hydrogens. Notice how on this carbon I did not put a pink notch to represent where a hydrogen would be, because there would be no hydrogen there. If you examine any of the carbons on that ring except for the carbon I just circled in gray, they would all have just 1 hydrogen because they all have a double bond and a single bond, which would be 3 out of the 4 possible. We cannot forget that there is a nitrogen on this compound, so we can just plop the N at the end. This is part 1 of the reading line structures video. There will be a second and a third part. The third part will have some more advanced examples that if you were in my class, you will definitely see.